Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Technogene. Our today's topic is how to detect fault in an underground cable. So, in an underground cable, when we installed the underground cable, it is usually installed in the form of ducts. So, we develop some ducts, and in the ducts, we lay the cables. So, there is very rare or little chance to have a fault in that system, but due to mishandling or some kind of when the roads or the system is in under construction, then during the construction process there may be a chance that the wire may cut, or some kind of fault may occur. So there are three types of fault which may occur in the transmission line. One is the open circuit, when the wire is completely disconnected and it is not connected with another wire or the ground. Then it is called an open circuit fault. Second one is short circuit fault. If the two wires are connected together, then wire 1 and wire 2, then this fault is known as short circuit fault. And in this fault is very dangerous, and it can create very problems in the system. And the third fault is that one conductor of the transmission line is cut and it is connected with the ground or the earth. So there are so we have to handle these three kinds of fault. So in order to remove this kind of fault, we need to find the location where the fault occur. In an underground cable, it is not possible to check the complete wire or to see the complete wire and detect the fault occurrence position. So we need some methodologies which can be used to detect where the fault is occurring. A simple and easiest way to detect the location of the fault is known as Murray loop test. In a Murray loop test is a simple Wheatstone bridge, and by using this Wheatstone bridge we can detect the fault. As you know that in a Wheatstone bridge we usually connect four different resistance, and we try to balance all the resistance, and the current in between two resistance is always equal to zero if the bridge is balanced. But if the bridge is not balanced, then we then there must be imbalance in the system. So in order to detect the fault, or the faulty location, faulty point, or the distance, uh, we we uh, we create a bridge in which we have two variable resistance, and the other side of the bridge is connected with the wire, with the wire. One side of the wire is connected with the one end of the bridge, and the other side of the wire is connected with the other end of the bridge. And when we switch on this switch, this galvanometer shows some deflection, and by adjusting the value of A and B we can balance the whole system, and this galvanometer can show reading at zero level or zero voltage. Once we get the zero voltage, then we can implement a simple mathematical formula and find the length of the system. So in a simpler way, we modify the circuit is by this mechanism, that the length the overall length of the system is LA plus LB. LA is the sending end length, and then the LB is the length of the wire which is returning back. As you know that the when there is a short circuit occur when two wires are connected, then the wire 1, starting end of the wire 1 till the short circuit is length A, and the ending end of the from the short circuit till the ending end of the second wire is known as B. So we can label it as LA and LB, and at the faulty location the distance would be LX. And the based on these three values we can calculate the fault. So mathematical formula of the system would be R2 over R1. If you see this figure, we have R2 and R1. So the ratio between R2 and R1 should be equal to the ratio between these two resistance. So the ratio between R2 and R1 is equal to RA plus RB minus Rx. Look at this one. We have the resistance of LA is RA, resistance of LB is RB, and the resistance of LX is Rx. So the overall resistance of the above side would be Ra plus Rb minus Rx would be the resistance of the above side, and the overall resistance of the lower side is Rx. This is the overall resistance of the lower side. So if we simplify this formula, then we have R2 into Rx is equal to R1 Ra plus R1 Rb minus R1 Rx. So by simplifying overall formula, then we can calculate Rx, and Rx is R1 over R1 plus R2 into Ra plus Rb. But in this given situation, we can measure Ra, La, Lb, but we cannot measure Ra and Rb. So we need to change this formula and change these values of Rx and Rx, Ra and Rb into La, Lb and Rx. So as you know that the resistance in the power system normally we calculate is R is rho L over A, where rho is the resistivity of the system and L is the length of the system and A is the area of the conductor. So if we put these values in Rx and in Ra and Rb, then we have rho x Lx over Ax, and then we have rho A La over Aa and rho B Lb over Ab. So if we take common rho x Ax, rho A Aa, rho B Ab, as you know that the conductor is same, so the rho and A of every side of the conductor is same, so we can cancel out rho and A. So the overall formula is Lx is equal to R1 over R1 plus R2 into La plus Lb. So from this formula we can calculate the unknown resistance. However, in the multi-core system, we can modify this formula as Lx is equal to 2 times R1 into L. As you know that length of La and Lb is the total length of the wire. So it can be represented as 2 times L. So divided by R1 plus R2. We are labeling La and Lb as L, and because both the lengths are same, so we are putting 2 times L in this system. So this is an example that the Murray loop test set in figure 5.18. This is the figure. Consists of two conductors of the same material and same cross-sectional area. Both cables are connected at 5,280 feet from the test setup at the cable terminal. The bridge is balanced when R1 is 100 ohm and R2 is 300 ohm. Find the distance from the ground fault to the test setup. So our formula is Lx is equal to 2 times R1 L over R1 plus R2. So when we put value of the R1, L, R1 and R2, the overall distance which is calculated is 240 feet. So this distance is 240 feet. That means the fault from the test setup, the distance between the fault and the test setup is 240 feet. So if we dig at the 240 point, we can find the fault. Second way of detecting the fault is Worley loop test. It is basically a modified version of Murray loop test, and it is much more accurate as compared to the Murray loop test. And in this test, the basic circuit diagram of this test is like this one. Now we are using three resistors R1, R2 and R3, and we are going to calculate the fault, and this fault is a ground fault. So so we use switch, and we can change the position of the switch. There are two possibilities: one when the switch is in A position and when the switch is in B position. If the switch is in A position, that means we have R1, R2 and R3, and the overall resistance A from this point to this point is basically RA plus RB. And if we connect switch B, then we have from this point we have two resistance R3 and Rx, because this point B point is basically ground, and it is technically connected with this point. So if we draw the line like this one, uh, like this, so B point is directly connected with this point. So it shows that now we have R3 and Rx in one side, and RA plus RB minus Rx in the other side. So by changing these values, we can calculate the overall value of the system. So if in the case 1, when the switch is at A position, the above side ratio of the resistance should be equal to the lower side of the ratio of the resistance. So the above side ratio of the resistance is basically R2 over R1, and the lower side resistance is basically this side resistance divided by this side resistance. So this side resistance is Ra plus Rb, and this side resistance is R3. So this formula is only valid when the system is in balanced condition. So by when we get this formula, when we simplify this formula, then we can get Ra plus Rb is equal to R2 R3 over R1, this form, and now we have to calculate Ra and Rp, because the unknown resistance, the unknown location which we need to measure is Rx. So now we need some formula related to Rx. When the switch is at position B, when the switch is at position B, this B point is indirectly connected with this ground. So it shows that the above side resistance is R2 and R1. However, the lower side resistance of this side, this up till this point, is basically R1 plus RB minus Rx, and this point resistance is R3 plus Rx. So when we apply the Wheatstone bridge, then formula, that based on this formula, it gives us the information that R2 over R1, the above side resistance is equal to the lower side resistance ratio. So it is R2 over R1 is equal to Ra plus Rb minus Rx divided by Rx plus R3 plus Rx. So if we simplify this formula and try to calculate a value of the Rx, then Rx is equal to R1 into Ra plus Rb minus R2 R3 over R1 plus R2. So both the values of Ra and Rb is also unknown. And this unknown value can be calculated from this one, that Ra plus Rb is equal to R2 plus R3 over R1. So if we calculate the value of R1 plus R2, then we can calculate the value of Rx, and from Rx we can calculate the value of Lx. So there is another example. In the Welle loop test set consists of a defective conductor and a healthy conductor connected at the cable terminal located at 10 miles from the test setup. The cable has a resistance of 0.5 ohm per 100,000 feet. When the switch is in position A and the circuit is balanced, the balancing resistance is R3 is equal to 100 ohm. When the switch is at B, the circuit is rebalanced and the balancing resistance is high. So it means that when the switch is at A position, the balancing resistance is this one, and the switch is at B position, the balancing resistance is this one. So so when the switch is in A position, the mathematical formula is this one: R1 plus RB is equal to R2 R3 over R1. So when we put the values of R1, R2 and R3, we can calculate this value, and this value is basically R1 Ra plus Rb. Now we need to calculate Rx. So Rx is equal to R1 into Ra plus Rb minus R2 R3 over R1 plus R2. So we have the value of Ra plus Rb. When we put the overall value of these resistance, we can calculate the unknown resistance is 0.67. So based on this value in this example, it shows that the resistance of the cable is 0.05 ohm per thousand feet. So when we want to calculate the overall resistance when distance, then we have 0.67 into 1000 divided by 0.05. So it is almost 13,333 feet. So this is basically the faulty point. Now the second topic which you need to understand is the skin effect. In the skin effect, if you know the basics of electrical system, then when the DC current flow in a conductor, the current is uniformly distributed in all over the conductor. But when the AC current passes through the conductor, the due to the magnetic flux intensity, the current in the center becomes zero, and the current tends to flow in the boundary of the conductor. So the current tend to follow more densely near the outer surface of the conductor than the near center. This phenomena is basically represented by skin effect. So due to the skin effect, the overall power consumption or the effective resistance of the system is disturbed, and this effective resistance of the conductor can be calculated is equal to the R effective is equal to P losses in the conductor divided by I square R. But this skin effect is dependent on the quality of the material. If the material internal resistance is increased, then the value of the skin effect is decreased. So in case of copper, the skin effect is larger than in case of aluminium. So the factors which affects skin effect is the frequency. Due to the increase in the frequency, the quality of the skin effect also increase. Similarly, the diameter. If the diameter of the if the diameter increase, then then the skin effect also increase. So we have to select specific diameter where the skin effect is minimum. Similarly, skin effect is also affected by the shape of the conductor. So we have if we have a solid conductor, then the skin effect is greater. But if we have number of conductor in the form of strands, then the skin effect will be reduced. Similarly, we have the skin effect also dependent on the material. If the permeability of the material is increased, then the skin effect also increase. And permeability is basically the capability of the conductor to support magnetic flux. So these are the four parameters by which the skin effect is skin effect may be disturbed, may be improved. So how to reduce skin effect? So by some mathematical calculation, it is concluded that if the frequency of the system is 50 hertz or less, then the skin effect in the conductor is almost negligible. And secondly, if the diameter of the conductor is less than 1 centimeter, then the skin effect is almost neglectable. So by using ACSR, aluminium conductor steel reinforcement, we usually in our usual practice that we did not increase the the diameter of the single conductor is always less than 1 centimeter. And the second thing is in the second is the frequency which we usually use is either 50 hertz or 60 hertz, and these are effective frequency in the power system, because in these frequency the effect of the skin effect is minimum. So for the case of DC, we want the current to be passing all over the conductor, but due to the skin effect, the current tends to flow in the surface of the conductor, and the internal conductor in the internal conductor the current is not flow. Now the second effect is known as proximity effect. Proximity effect is quite similar to the skin effect, because the skin effect is basically the non-uniformity or the uniformity of the current in the conductor, but the proximity effect is usually occur due when current is flowing in two conductors and the effect of the one conductor is disturbing the uniformity of the current in the second conductor. Similarly, the second conductor is affecting the first conductor. So this effect is known as proximity effect. So there are two chances. If the current, if in the both conductor the current is in the same direction, then the common region, at the common region the current is almost neglectable, and the outer region current, the value of the current is increased. While if in the second case, if the current in the two conductors are moving in opposite direction, then the point at which in the common region the current is increased, while the outer region the current is decreased. सो इन द फिगर आप ये देख सकते हो कि ये देखो, जब करंट सिमिलर डायरेक्शन में जा रहा है तो ये एक दूसरे को रिपेल करेंगे, यानी कि जो मैग्नेटिक फ्लक्स है वो एक दूसरे को रिपेल करेगा, तो आउटर सरफेस पे करंट, ऑपोजिट साइड पे करंट फ्लो करेगा, लेकिन इनर सरफेस पे नहीं फ्लो करेगा। जबकि अगर दोनों कंडक्टर का करंट की डायरेक्शन ऑपोजिट है तो क्या होगा कि जो इनर सरफेस है उसमें करंट फ्लो करने लग पड़ेगा, जबकि आउटर सरफेस पे नहीं फ्लो करेगा, क्योंकि जो मैग्नेटिक फ्लक्स अपीयर होगा वो एक दूसरे को अट्रैक्ट करना शुरू करता है। So the in proximity effect is also dependent on frequency, because when the frequency increase, this effect also increase. Similarly, it also depend on the diameter. With the increase in the diameter, the proximity effect also increase. Similarly, the structure of the conductor, in the solid conductor, the proximity effect is greater. But if we have multiple strands of conductor, then the proximity effect can be reduced. The fourth point is the material. If it dependent on the ferromagnetic capability of the material. If the ferromagnetic capability of the material is larger, then the proximity effect is also larger. But if the ferromagnetic capability is lesser, then the proximity effect is lesser. So in order to reduce the proximity effect, we usually use aluminum conductors, steel reinforced. Uh, uh, and why we are using this? Because in the aluminum conductor we have the outer conductor covered with the aluminum, and in the center we have the steel for reinforcement, and when the proximity effect occur, so due to the center steel conductor, this proximity effect is reduced. So yeah, hopefully you understand the basic concept of the faults and the skin effect. Jazakallah. Stay blessed. Allah.